For the case of more than one variable, see conic section or quadratic form. In elementary algebra, a quadratic equation is any equation having the form where x represents an unknown, and a, b, and c represent known numbers such that a is not equal to 0. If a equals 0, then the equation is linear, not quadratic. The numbers a, b, and c are the coefficients of the equation, and may be distinguished by calling them, respectively, the quadratic coefficient, the linear coefficient and the constant or free term. Because the quadratic equation involves only one unknown, it is called univariate. The quadratic equation only contains powers of x that are non-negative integers, and therefore it is a polynomial equation. And in particular it is a second-degree polynomial equation since the greatest power is 2. Quadratic equations can be solved by a process known in American English as factoring and in other varieties of English as factorizing. By completing the square, by using the quadratic formula, or by graphing. Solutions to problems equivalent to the quadratic equation were known as early as 2000 BC. Solving the quadratic equation. A quadratic equation with real or complex coefficients has two solutions, called roots. These two solutions may or may not be distinct, and they may or may not be real. Factoring by inspection, it may be possible to express a quadratic equation x2 plus bx plus c equals 0 as a product equals 0. In some cases, it is possible, by simple inspection, to determine values of p, q, r, and s that make the two forms equivalent to one another. If the quadratic equation is written in the second form, then the zero-factor property states that the quadratic equation is satisfied if px plus q equals 0 or rx plus s equals 0. Solving these two linear equations provides the roots of the quadratic. For most students, factoring by inspection is the first method of solving quadratic equations to which they are exposed. If one is given a quadratic equation in the form x2 plus bx plus c equals 0, the sought factorization has the form, and one has to find two numbers q and s that add up to b and whose product is c. As an example, x2 plus 5x plus 6 factors is. The more general case where it does not equal 1 can require a considerable effort in trial and error guess and check. Assuming that it can be factored at all by inspection, except for special cases such as where b equals 0 or c equals 0. Factoring by inspection only works for quadratic equations that have rational roots. This means that the great majority of quadratic equations that arise in practical applications cannot be solved by factoring by inspection. Completing the square. The process of completing the square makes use of the algebraic identity, which represents a well-defined algorithm that can be used to solve any quadratic equation. Starting with a quadratic equation in standard form, x2 plus bx plus c equals 0, divide each side by a, the coefficient of the squared term. Subtract the constant term c, a from both sides. Add the square of 1/2 of b, a, the coefficient of x, to both sides. This completes the square, converting the left side into a perfect square. Write the left side as a square and simplify the right side if necessary. Produce two linear equations by equating the square root of the left side with the positive and negative square roots of the right side. Solve the two linear equations. We illustrate use of this algorithm by solving 2 by 2 plus 4x minus 4 equals 0. The plus-minus symbol, plus or minus, indicates that both x equals minus 1 plus square root 3 and x equals minus 1 minus square root 3 are solutions of the quadratic equation. Quadratic formula and its derivation. Completing the square can be used to derive a general formula for solving quadratic equations, called the quadratic formula. The mathematical proof will now be briefly summarized. It can easily be seen, by polynomial expansion, that the following equation is equivalent to the quadratic equation. Taking the square root of both sides, and isolating x, gives Some sources, particularly older ones, use alternative parameterizations of the quadratic equation such as x2 plus 2bx plus c equals 0 or x2 minus 2bx plus c equals 0, where b has a magnitude 1/2 of the more common one, possibly with opposite sign. These result in slightly different forms for the solution, but are otherwise equivalent. A number of alternative derivations can be found in the literature. These proofs are simpler than the standard completing the square method, represent interesting applications of other frequently used techniques in algebra, or often insight into other areas of mathematics. One property of this form is that it yields one valid root when r equals 0, while the other root contains division by 0, because when r equals 0, the quadratic equation becomes a linear equation, which has one root. By contrast, in this case the more common formula has division by 0 in both cases. Reduced quadratic equation. It is sometimes convenient to reduce a quadratic equation so that its leading coefficient is 1. This is done by dividing both sides by a, which is always possible since a is non-zero. This produces the reduced quadratic equation, where p equals b, a and q equals c, a. This monic equation has the same solutions as the original. The quadratic formula for the solutions of the reduced quadratic equation, written in terms of its coefficients, is discriminant in the quadratic formula. The expression underneath the square root sign is called the discriminant of the quadratic equation, and is often represented using an uppercase D or an uppercase Greek delta. A quadratic equation with real coefficients can have either one or two distinct real roots, or two distinct complex roots. In this case, the discriminant determines the number and nature of the roots. There are three cases. If the discriminant is positive, then there are two distinct roots, both of which are real numbers. For quadratic equations with rational coefficients, if the discriminant is a square number, then the roots are rational. In other cases they may be quadratic irrationals. If the discriminant is 0, then there is exactly one real root, sometimes called a repeated or double root. If the discriminant is negative, then there are no real roots. Rather, there are two distinct complex roots, which are complex conjugates of each other. In these expressions, I is the imaginary unit. Thus the roots are distinct if and only if the discriminant is non-zero, and the roots are real if and only if the discriminant is non-negative. Geometric interpretation. The function f equals x2 plus bx plus c is the quadratic function. The graph of any quadratic function has the same general shape, which is called a parabola. The location and size of the parabola, and how it opens, depend on the values of a, b, and c. As shown in Figure 1, if a greater than 0, the parabola has a minimum point and opens upward. If a less than 0, the parabola has a maximum point and opens downward. The extreme point of the parabola, whether minimum or maximum, corresponds to its vertex. The x-coordinate of the vertex will be located at, and the y-coordinate of the vertex may be found by substituting this x value into the function. The y-intercept is located at the point. The solutions of the quadratic equation x2 plus bx plus c equals 0 correspond to the roots of the function f equals x2 plus bx plus c, since they are the values of x for which f equals 0. As shown in Figure 2, if a, b, and c are real numbers and the domain of f is the set of real numbers, then the roots of f are exactly the x-coordinates of the points where the graph touches the x-axis. As shown in Figure 3, if the discriminant is positive, the graph touches the x-axis at 2 points, if 0, the graph touches at 1 point, and if negative, the graph does not touch the x-axis. Quadratic factorization. The term is a factor of the polynomial if and only if r is a root of the quadratic equation. It follows from the quadratic formula that in the special case b2 equals 4ac where the quadratic has only one distinct root, the quadratic polynomial can be factored as graphing for real roots for most of the 20th century. Graphing was rarely mentioned as a method for solving quadratic equations in high school or college algebra texts. Students learn to solve quadratic equations by factoring, completing the square, and applying the quadratic formula. Recently, graphing calculators have become common in schools and graphical methods have started to appear in textbooks, but they are generally not highly emphasized. Being able to use a graphing calculator to solve a quadratic equation requires the ability to produce a graph of y equals f, the ability to scale the graph appropriately to the dimensions of the graphing surface, and the recognition that when f equals 0, x is a solution to the equation. The skills required to solve a quadratic equation on a calculator are in fact applicable to finding the real roots of any arbitrary function. Since an arbitrary function may cross the x-axis at multiple points, graphing calculators generally require one to identify the desired root by positioning a cursor at a guessed value for the root. The calculator then proceeds, by an iterative algorithm, to refine the estimated position of the root to the limit of calculator accuracy, avoiding loss of significance. Although the quadratic formula provides what in principle should be an exact solution, it does not, from a numerical analysis standpoint, provide a completely stable method for evaluating the roots of a quadratic equation. If the two roots of the quadratic equation vary greatly in absolute magnitude, b will be very close in magnitude to, and the subtraction of two nearly equal numbers will cause loss of significance or catastrophic cancellation. A second form of cancellation can occur between the terms b2 and -4ac of the discriminant, which can lead to loss of up to half of correct significant figures. Examples and applications. The golden ratio is found as the solution of the quadratic equation. The equations of the circle and the other conic sections, ellipses, parabolas, and hyperbolas, are quadratic equations in two variables. Given the cosine or sine of an angle, finding the cosine or sine of the angle that is half as large involves solving a quadratic equation. The process of simplifying expressions involving the square root of an expression involving the square root of another expression involves finding the two solutions of a quadratic equation. Descartes' theorem states that for every four kissing circles, their radii satisfy a particular quadratic equation. The equation given by Fuss' theorem, giving the relation among the radius of a bicentric quadrilateral's inscribed circle, the radius of its circumscribed circle, and the distance between the centers of those circles, can be expressed as a quadratic equation for which the distance between the two circles' centers in terms of their radii is one of the solutions. The other solution of the same equation in terms of the relevant radii gives the distance between the circumscribed circle's center and the center of the x-circle of an x-tangential quadrilateral. History. Babylonian mathematicians, as early as 2000 BC, could solve problems relating the areas and sides of rectangles. There is evidence dating this algorithm as far back as the 3rd dynasty of Ur. In modern notation, the problems typically involved solving a pair of simultaneous equations of the form, which are equivalent to the equation. The steps given by Babylonian scribes for solving the above rectangle problem were as follows. Compute half of p, square the result, subtract q, find the square root using a table of squares, add together the results of steps and to give x. This is essentially equivalent to calculating. Geometric methods were used to solve quadratic equations in Babylonia, Egypt, Greece, China, and India. The Egyptian Berlin papyrus, dating back to the Middle Kingdom, contains the solution to a two-term quadratic equation. In the Indian Sulba Sutras, circa 8th century BC, quadratic equations of the form x2 equals c and x2 plus bx equals c were explored using geometric methods. Babylonian mathematicians from circa 400 BC and Chinese mathematicians from circa 200 BC used geometric methods of dissection to solve quadratic equations with positive roots. Rules for quadratic equations were given in the 9 chapters on the mathematical art, a Chinese treatise on mathematics. These early geometric methods do not appear to have had a general formula. Euclid, the Greek mathematician, produced a more abstract geometrical method around 300 BC. With a purely geometric approach, Pythagoras and Euclid created a general procedure to find solutions of the quadratic equation. In his work Arithmetica, the Greek mathematician Diophantus solved the quadratic equation, but giving only one root, even when both roots were positive. In 628 AD, Brahmagupta, an Indian mathematician, gave the first explicit solution of the quadratic equation x2 plus bx equals c as follows. To the absolute number multiplied by 4 times the coefficient of the square, add the square of the coefficient of the middle term, the square root of the same, less the coefficient of the middle term, being divided by twice the coefficient of the square is the value. This is equivalent to the Bakshali manuscript written in India in the 7th century AD contained an algebraic formula for solving quadratic equations, as well as quadratic indeterminate equations. Inspired by Brahmagupta, developed a set of formulas that worked for positive solutions. Al-Khwarizmi goes further in providing a full solution to the general quadratic equation, accepting 1 or 2 numerical answers for every quadratic equation, while providing geometric proofs in the process. He also described the method of completing the square and recognized that the discriminant must be positive, which was proven by his contemporary, Abd al-Hamid ibn Turk, who gave geometric figures to prove that if the discriminant is negative, a quadratic equation has no solution. While Al-Khwarizmi himself did not accept negative solutions, later Islamic mathematicians that succeeded him accepted negative solutions, as well as irrational numbers as solutions. Abu Kamil Shuja ibn Aslam in particular was the first to accept irrational numbers as solutions to quadratic equations or as coefficients in an equation. The 9th century Indian mathematician Sridhara wrote down rules for solving quadratic equations. The Jewish mathematician Abraham Bar Hiyya Harnasi authored the first European book to include the full solution to the general quadratic equation. His solution was largely based on Al-Khwarizmi's work. The writing of the Chinese mathematician Yang Hui is the first known one in which quadratic equations with negative coefficients of x appear, although he attributes this to the earlier Lu Yi. By 1545 Gerolamo Cardano compiled the works related to the quadratic equations. The quadratic formula covering all cases was first obtained by Simon Stevan in 1594. In 1637 René Descartes published La Géométrie containing the quadratic formula in the form we know today. The first appearance of the general solution in the modern mathematical literature appeared in an 1896 paper by Henry Heaton.